there's some excellent stuff at the end of chapter 5, as I've referred to there in the reading notes. There's a good step-by-step tutorial in section 5.4. And then I think a good set of exercises, the SAGE exercises 5.5. So we'd be aiming to be able to work through those in the lab session on Friday afternoon as well. Okay.
So just start this off. Yes, so Rebecca was telling me that some of the. So hopefully it'll be okay from now on. I think it's just due to the Wi-Fi cutting in and out, so there might be dropping
Video or the audio sometimes. But, okay. So, chapter 5 on permutation groups and dihedral groups. So first of all, let's just look at the reading notes that I just drew up here for chapter 5. So this kind of just goes through, tells you a little bit about what the main topics are, and just a kind of warning or two, or a point or two about them. So the two main topics, permutation groups and dihedral groups. Now we'll go through it in detail, but very briefly, permutation groups are groups made up of things called permutations. Permutations are particular types of things, are kind of fundamental type of object in combinatorics, the mathematics that looks at the possibilities of arrangements and combinations and so on. So it's an important topic. And a permutation, well, we say a permutation of n symbols or n objects is any bijection from this set to itself. So this set is just the set of the labels 1, 2, up to n. There's nothing special or significant about the fact we're using numbers. This could literally be any set of n distinct labels. You could use the letters A, B, C, D, E, F, whatever. It's just convenient and traditional to use the first few positive integers as these. So that's what a permutation is. So a permutation group is some kind of group in which the elements are permutations, and the operation, group operation, is composition. So, okay, because a permutation is a function from this set to itself. So the natural operation there, when you've got functions from a set to itself, is just to compose these operations one after another. And that gives you the group operation. And the beginning of the chapter goes through various kind of types of notation that we can use for permutation. So that's one key point to be to pick up on. So to appreciate the difference between two-line and cycle notations. So we're going to be going through that. And then probably the most significant result is theorem 5.9, which I've said there gives a near canonical form, or really a canonical form for representing permutations as product of disjoint cycles. What we'll see is, when we're looking at the different types of notation, we'll see this kind of issue where for any given permutation, there's a number of different ways you might represent it with notation as products of other permutations. And initially, anyway, you kind of struggle to see, well, how do I know if I'm looking at a big product of permutations, how do I know if it's equal to another big product of permutations? Is there some kind of unique way of representing these, or a unique way of simplifying them down to some kind of canonical representation? Well, that is provided by this representation as products of disjoint cycles. Okay. Now, permutations will be around for a lot of our study of group theory. They're very rich in that whatever kind of a group theory concept or feature you might care to consider, you will be able to find examples of that exhibited by groups of permutations. Okay? And indeed, and the reason for that is later on when we're looking in detail at isomorphisms. So isomorphisms is a way that you make it very concrete and formal, the idea of two groups being equivalent. Okay? So two groups, although they might be composed of quite different mathematical objects, they might necessarily, they might nevertheless be equivalent as groups.
Well, isomorphisms is the concept that allows us to formalize that and state that rigorously. And we'll see later on there's a result called Cayley's theorem, which basically says if you're given any group at all, you can find a group of permutations that is equivalent to it, that exhibits the same group theory structure or group theory features as whatever the initial group started with. So in that sense, they're very rich. Every group is equivalent to some group of permutations. Now, in some ways, that might make you think, oh well, then the universe of groups must be very simple, because if every group is equivalent to a permutation group, then all we need to do is study the permutation groups and understand them. But really, that's not really the result of that statement. It isn't saying that the universe of groups is very simple because everything is equivalent to permutation groups. It's saying that permutation groups are as complicated as the full universe of groups. Okay. Because within permutation groups, you can find any possible group theory feature and structure. Okay? So even something which looks deceptively simple, like groups of permutations, really, there's as they can get as complicated as possible. So. Then the second topic, which as we get started soon, we'll be able to look at are dihedral groups. So these are very particular kinds of groups. These correspond to the symmetry groups of various regular n-sided polygons. So n-sided polygons are things like the isosceles triangle, regular triangle, square, regular pentagon, hexagon, etc. Okay. So these things have interesting symmetry properties, and they provide us with a nice family of groups. And they will be represented as permutation groups. So we're kind of seeing an example of Cayley's theorem kind of here in that the way we talk about dihedral groups, and certainly the way we operate with them in Sage, is the form of their permutation. Again, chapter 5 and exercises, loads of exercises there, a good lot of kind of practical computational example ones at the beginning, moving on to more kind of substantial proof-oriented problems later on in the list. And the Sage exercises for the lab on Friday, again, some very good stuff in the book there that we'll be able to work with. And this important warning that you'll need to keep in mind, I think you encountered this a few weeks ago when we did some initial work with permutations. When you've got two permutations, when we multiply them together in a group, what we're really doing is we're composing the functions. Now, normally in mathematics, if sigma and tau here, if those are functions, and you see the functions being multiplied together here, well, what we mean is the composition of these two functions. And normally, almost universally in mathematics, when you see a composition of functions written down, what we mean is that the function tau is applied first, the one on the right is applied first, and then sigma is applied after it. Okay, that's how you figure out the action of this composite function on any particular argument. Remember, these are permutations, so they'll be acting on the labels 1 to n, quote, whatever type of permutation that they are. However, within Sage operates with exactly the opposite convention. So if you have two permutations, sigma and tau, stored as variables in a Sage session, and as elements of a permutation group, if you multiply them together, this is the group operation, which is still composition. However, the composite sigma times tau, the composition that is represented is the function sigma applied first, and then tau applied to the result of applying sigma. Okay, so you just have to keep that in mind, that if you're moving between pen and paper stuff and calculations using Sage, everything gets flipped. The order of evaluation of the compositions gets flipped. So that's something you need to keep in mind. Okay, so let's move through the chapter, and we'll expand on some of these points and explain them. Okay, so the initial example that it gives there on the very first page on 81 is recalling symmetries of the triangle. And this, in a way, is an initial example of dihedral groups as well.
They were called the symmetries of the regular triangle. So here's our regular triangle. That's a very irregular sketch, but let's just assume that's an isosceles triangle. We imagine it's centered at the origin. Okay, and there are 6 different symmetries that this has. Okay, 6 different symmetries that we consider. There's the identity, E, the rotation, anticlockwise by 2 pi over 3, by 1/3 of a full turn. Then there's the rotation anticlockwise by 4 pi over 3.
2/3 of a full turn. We don't consider rotation by 3/3 of a full turn because that's just the same as the identity. And we often mention the identity in the same breath as the rotations because really the identity is a rotation. It's a rotation by an angle of 0 or by a full turn. And then there are 3 reflections. We've got reflection in the axis. There are 3 reflectional axes of symmetry of the regular triangle. They are the ones that go through each vertex. They're the line joining each vertex with the center of the triangle. Okay. It's a little bit. So I've drawn the 3 reflectional axes there. We might number those as say axis 1, axis 2, axis 3. And it makes sense to have a compact notation. So we use E for the identity, R for the basic rotation. We don't need another symbol for the other type of rotation because it makes sense to think of that as R squared. Of course, the square is referring to the operation, which is composition. So R composed with R. Apply the rotation and follow it with another rotation. And then let's use sigma 1, sigma 2, sigma 3 for these reflections of the axis. And so far, there are no permutations in view. We're thinking of the group, so this is the group D3. Group D3 just consists of these 6 objects. And the objects are transformations of the plane. Okay? But there's another way that we can think of this, and the way we can encode all the information here. And this is through the use of permutations. Okay? And this can be done by introducing some kind of a labeling of. You just need to label the essential features of the polygon. Here we've labeled the vertices. Equally well, you can do it by labeling the edges as well. But we're going to proceed by labeling the vertices. And each of our transformations can be thought of as all we need to do is just record its action on the vertices. Okay? So the identity transformation, well, that's the transformation of the plane where everything remains in the same spot. And so the action of the identity on the vertices is simply to send A to A, B to B, and C to C. Okay? So here we're looking at we've got this 2-line notation. So we have the argument on the first line and the value, the image of the transformation applied to that argument on the second line. And the rotation R, well, if rotation is going, I've said anti-clockwise, so A moves to position C, B moves to position A, and C moves to position B. All right, I rotate anti-clockwise. And if you do R squared, that can be represented as A goes to B, B goes to C, C goes to A. All right. And then the 3 reflections, the sigma 1, well, see the reflection axis, sigma 1, is going through axis C. That's axis 1 there. So can you see that? Yeah. It's going through axis C. So
That means that C is left unchanged because it's on the line of reflection, and the other two swap positions. A goes to B, and B goes to A. Similarly, for sigma 2, sigma 3, sigma 2 is the line that fixes A, B goes to C, C goes to B. Sigma 3 will be the line that fixes B, so B goes to B, A goes to C.
Okay. Notice I've hesitated to write that E equals this or R equals this, rather just this kind of, there's a correspondence between each of these transformations of the plane and each of these what are called two-line permutations. So these things here we might call two-line permutations. On one hand, we can think of this group of symmetries of the triangle, the dihedral group, as consisting of transformations of the plane, things you do to the plane. On the other hand, we can think of them in this much more combinatorical way, as just recording the information of what they do to the vertices. And that's enough to kind of uniquely represent in this context. Okay? And we see them as permutations on three labels. But of course, equally well, you know, I've used the letters A, B, C. Equally well, we could have numbered the vertices 1, 2, 3, and so on. It's not really important. All that we have is just some set of distinct labels. So, any questions about just that initial example? Or is that okay? Okay. So we then have the general definition of a permutation and the group of all permutations. So this is the definition in section 5.1. So in general, permutation, so this is more or less exactly what's written on the summary reading notes sheet. Permutation on n symbols is a bijective function. From the set of n labels, usually represent as a set of numbers 1 through n, a bijection from this set to itself. Okay? So it's a one-to-one and onto function from this set to itself. The theorem, the first theorem, 5.1, says that S of n, which is the set of all permutations on n symbols, is a group. Okay. So the group operation, remember, is composition. Is a group under the operation of composition. The proof of that is there's nothing too hard in the proof. It's really just a straightforward observation that since we're using functions from a set to itself, since the operation is composition, composition of functions is automatically associative. We're considering all bijections. Well, any bijection has an inverse, and that the inverse is going from the set to itself. And by definition of the inverse of the bijective function, the inverse is also a bijective function. So the inverse is also there. There's certainly identity element. The identity element is just the identity bijection that sends every element to itself. And so, okay. So it automatically satisfies the conditions of the group. And any such permutation can be represented by, can be denoted by its two-line notation. This is the first type of notation. It's the one we've been seeing in the triangle example. So you have the arguments 1, 2, 3, etc. along the top line up to n, and then you put the values, the image of, I'm going to call this permutation sigma. Under here we have sigma 1, the image of 1 under this permutation underneath 1, sigma 2 underneath here, etc. All the way up as far as the last image of the label n, sigma of n underneath there.
Now, the other part of theorem 5.1, which I haven't mentioned yet, is theorem 5.1 also says what the order of this group is. Okay. So how many such permutations are there? Well, indeed, it says in the notes that he leaves the proof of that, proof of the order as an exercise.
Well, we can answer this just by considering this two-line notation here. How many different possible ways are there of writing down this two-line permutation symbol? Well, we need to keep in mind that we have to have it being a bijection. Okay, so you can start at any position. May as well start here on the left. How many possible choices are there for the value of sigma 1? So how many, if we think of all the permutations, what are the different options for the image of 1? Well, clearly, we could send 1 to any of the elements here. Okay, so there are n choices for the value of sigma 1. Now, how many choices are there for the value of sigma 2? Well, on its own, considered as a question in isolation, how many choices are there for the image of 2? Well, again, there's n choices. However, if we're counting up our choices, and if we've already assigned a choice to sigma 1, because we need to keep it a bijection, it has to be 1 to 1, we can't send 2 to the value sigma 1 that we've already put down. So having chosen the image sigma 1, there are now only n-1 choices left for sigma 2. Okay? So n possible choices here, n-1 possible choices here. What about sigma 3? Well, if we're accumulating the decisions here, we've already chosen sigma 1, already chosen sigma 2. There will only be n-2 choices here. Okay? You keep looking at how to build up the symbol. By the time you get to the last one, what is sigma of n? Well, you would have already chosen the n-1 images before. So there'll be, and you're keeping it a bijection each time, so there's only one symbol left over. That has to be the answer that goes in here for sigma n. So you look at all those contingent choices depending on each other. How many different ways are there of choosing those choices? Well, there's n choices for the first slot, n-1 for the second as well. So the total number of possibilities is the product of all those intelligent choices. So n times n-1. So that's what gives you the n factorial. Okay. How many such permutations are there? I.e., how many ways of bijectively completing the 2-9 notation well, that equals n factorial. Okay? N choices for the first position, n-1 for the second, and so on. If we didn't have the condition that it had to be a bijection, there would be n choices for the first one, n choices for the second one. So if we just wanted any old function from the set 1, 2 up to n to itself, just n choices for here, n choices for here. So the total number of functions will be n to the power n. Okay? But that includes, most of those functions will not be bijections, because in there would be the function that sends everything to the value 1. That's if we chose 1 as the image for everything. But that is clearly not a bijection. So if we're just restricting to bijections, we've got n factorial possible choices. So this is this Sn is called, well, you could call it the group of all permutations on n symbols, but it's also called the symmetric as well. Okay? As distinct from a symmetry group. So a symmetry group is just a general thing, a group of symmetries of a certain kind of object. But the symmetric group refers to this set, this group Sn. Okay. So over the page, then on page 82, well, there's a number of examples of working with the 2-line notation. So they look at not the full symmetry group Sn, but they look at three particular permutations on 5 objects, and they're actually showing here that these actually form the subgroup, I believe. Yeah, because if you draw out this multiplication table for these 3 particular permutations, you find that it's a closed set under the operation of composition. Every entry in here, well, sorry, we'd have to take the identity as well. So as long as we include the identity as well, every entry in here is one of sigma, tau, or mu, or the identity. There are inverses for every object. In fact, every object is self-inverse. Sigma squared is the identity, tau squared is the identity, mu squared is the identity, and so on. It's automatically associative. So you've got the presence of the identity closed under the operation, presence of inverses, and it's associative as well. So that is a subgroup of S5. Got another example here, emphasizing. Okay, remember this is composition of functions. In general, composition of functions is not commutative, and that's indeed true for permutations. So this is a concrete example showing 2 permutations on 4 objects, composing them, and they've got different 2-line notation, so they're clearly not the same. Okay? So we do not expect composition of permutations to be commutative, okay? Just as we cannot expect general composition of functions to be commutative. Now this 2-line notation is grand as far as it goes. There's nothing particularly wrong with it, except that it is a bit cumbersome to work with all the time. I mean, if we always have 1, 2, 3, 4 written across the top, that's a bit wasteful writing that all the time. Really, we can understand that 1, 2, 3, 4 are always written across the top. So it's a bit of an overkill. And also, it's not particularly illuminating on the structure of the individual permutation. So there is a better type of notation. This is the cycle notation. Now, to understand the cycle notation, well, he goes through a discussion of it there in the text, but instead, I think I'll choose one of his examples here, and we'll just talk about it. And I'll just try and persuade you that cycle notation is a very natural way to think about permutations. Okay? So this is choosing one of his examples. So consider the permutation sigma 6 objects. So this example he uses in the middle of the page. So in its 2-line notation, it's here. So 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, 5 goes to 6, 6 goes to 5. Now this is a function, a bijective function from the 6 labels 1 through 6 to itself. So you can kind of get a picture for what's going on if we just consider the set of these 6 objects. So I've just got a blank cloud. I've just got the 6 objects hovering there in the cloud in no particular order. And by means of arrows, you can draw out the action of sigma. Okay? So what is sigma doing? Sigma sends 1 to 2. And it sends 2 to 4. And rather than looking at 3 at the moment, what I'm going to do is I'm going to continue this chain of arrows. So 1 got sent to 2, 2 gets sent to 4. Where does 4 go to? 4 goes to 3. Continuing on this chain of arrows. 4 gets sent to 3. What happens to 3? You look at the 2-line notation. 3 gets sent to 1. Okay. I don't need to look at what 1 gets sent to because I've already considered that. 1 gets sent to 2. Then there's 2 elements left, so just choose one of them to start with. What happens to 6? 6 gets sent to 5, and 5 gets sent to 6. Okay. Now I've chosen my colors carefully there. We can see now, for this permutation, it very naturally splits up into 2 sub-permutations, if you like. 2 fundamental structures. There's all this stuff going on over here, and there's all this stuff going on over here. Okay? What's going on over here does not interfere with what's going on over here, and vice versa. It's like the story of what's going on in sigma is made up of this little independent story here, and this little independent story here. Okay? So it's very natural. it's not really to do with the notation. It's inherent part of the permutation itself. Okay? So seeing this obvious decomposition of the full permutation into these smaller substructures, we very much want to capitalize on that and encode that into our notation and draw that feature out. Okay? So this leads us to represent sigma as follows. So what's going on with the red stuff? Well, the red stuff, we just need to record this information here. And we can record this information by just giving the chain of elements, a chain of arrows, just describing the chain. But the important thing to describe the chain, you can see there is no beginning or end. Remember, these are just 6 distinct labels. There's nothing particularly important about 1 over the choice of 2. So there is no, it's a closed loop. There is no start or end to it. What's important about the loop is the order in which the elements fall as you move around the loop. Okay? So we just need to record that in some sense. So let's start with 3 for no apparent reason. So 3 goes to 1, 1 goes to 2, 2 goes to 4, and we've reached the end of the cycle there. So we have this symbol to record what's going on there, and what's going on over here is 6, 5. 6 goes to 5, and 5 goes to 6. Okay? So these are examples of cycles. This is a 4 cycle, and this thing is a 2 cycle. 4 meaning it's a cycle of 4 elements, and 2 cycle meaning it's a cycle of 2 elements. 2 cycles also have special names. They're called transpositions. 2 cycle, interchanging the positions of 2 objects is called a transposition. Transposing 2 objects. So this is example of cycle notation. Okay? So a range of symbols like this, so 3, 1, 2, 4, say if we write that equal to tau, so tau is the permutation which cyclically permutes the labels 3, 1, 2, 4 in the order shown, and leaves all other elements unchanged. So by definition, sigma or tau of 5 is equal to 5. Tau of 6 is equal to 6. Now we introduce these things as permutations on 6 objects, so reasonably we shouldn't apply tau to any other argument other than 1, 2, 3, 4, 5, or 6. But by implication, this cycle, it cycles these elements around in the order shown, and it leaves everything else unchanged. Okay? So that's basically the idea of cycles. And this notation here for sigma, this is sigma represented as a product or a composition. Product meaning the group product as a product of disjoint cycles. Disjoint, so that's the idea that, you know, what's going on with the 5 and 6 is completely independent to what's going on with the 1, 2, 3, and 4. Okay, the 2 cycles don't interfere with one another. So I've written as a product of cycles. So this group operation here, this is the operation of composition. Okay, I've no symbol there for it, but it's in 5. But the fact that I'm writing down the product of those 2 cycles, it's within the symmetric group. So the operation is composition. And we notice something important. Because the 2 cycles are disjoint, they don't interfere with one another, composition of disjoint cycles is commutative. Okay? Because they don't interfere with each other. So I can permute these, and then I can permute these ones. Or if I want, I can cycle these ones around and then cycle those ones. because the two actions don't interfere with one another, it doesn't matter in what order I do them. Okay. The example given before, which showed that you can't have commutativity in general, you'll notice here that the sigma and tau, which didn't commute in this first example, they were not disjoint. So notice that sigma moves around 1 and 2. Well, in fact, it moves around all of them, 1, 2, 3, and 4. And so does tau. Tau changes the positions of all the arguments. So they are certainly not disjoint. The things that are involved in tau are also the things that are involved in sigma. So it might make a difference in what order the actions are performed. But if the actions are affecting completely separate stuff, it doesn't matter in what order you combine. Okay? So that was the other important point. Notice that disjoint cycles commute. So this sigma I have up above, equally I could write that as 5, 6 and 1, 2, 4, 3. Notice I've also demonstrated something else there. I've shown you the fact that you cycles, okay, I don't have to represent this one starting with 3 equally, I could represent it starting with 1. Okay. So that's why I said a near canonical form. So I haven't quite got a unique form for sigma, because already I've got 2 different strings representing sigma, but really they're kind of just trivial manipulations of each other. What is inherent, what is canonical, what is a unique representation of sigma is representing sigma as this cycle and this cycle. Okay? And that's what we can see in this product of disjoint cycle. So there's a couple of theorems which we kind of cycled through there, in a way, if you like. Theorem proposition 5.8 on page 84, that proves formally that 2 disjoint cycles commute. And theorem 5.9 proves formally that every permutation can be written as a product of disjoint cycles. Okay. Any questions so far on what we've done? So you can see how this kind of stuff is mostly a matter with just arriving at the correct notation to think about permutations, and spotting this idea that decomposition into disjoint cycles is quite important. Okay, so what does he do in the rest of the chapter? Well, I might get to talking about the dihedral group material today, but I'll leave you to read over that, and we'll talk a little bit about that on Friday morning before going through the exercises. What he then goes on to talk about in the chapter is the notion of transpositions. Okay, so this representation as product of disjoint cycles is important. It also turns out thinking about how things can be represented as products of transpositions is also important. There's a very natural way in which you can take any cycle. So here we have a general cycle. This is the cycle of the elements A1, A2, A3, etc. up to AN. It's taking these n labels and cycling them around. It decomposes into a product of transpositions here in a very natural way. Okay? You can think of, so this here just sends A1 to A2, sends A2 to A3, and so on. We can decompose that as, first of all, swapping the positions of A1 and A2, then swapping the positions of A1 and A3, then swapping the positions of A1 and A4, and so on. Okay. Performing all those operations, all these individual transpositions in sequence like that, that carries out that full cycling of elements there. Okay. But now, when you represent a cycle like that, a cycle is a product of these transpositions, note that these transpositions are no longer disjoint, okay? Because every one of them involves A1. Okay? So they're certainly not represented as a product of disjoint cycles. So it may be, and it will be, that there could be many different ways of representing this cycle as a product of transpositions. However, there is something that is always always the same. For instance, so here in this example, here's a permutation. It's the product of a 2-cycle and a 3-cycle here. He's able to represent it as the product of these 3 transpositions, and also as the product of these 5 transpositions. So this is kind of confusing and kind of, obfuscating a bit. So I can represent this permutation as this or this. Well, what is shared between these two is the parity of the number of transpositions. There's an odd number of transpositions here, namely 3. There's also an odd number of transpositions there, namely 5. That feature is consistent. Okay? So any particular permutation, either all of its representations as products of transpositions will be containing an odd number of transpositions, or it will always be an even number. Okay? So how that's proved, he proves that in 2 steps. Lemma 5.14, first of all, proves it for the case of the identity. Okay? He shows that the identity, if we're to represent the identity transformation as a product of transpositions, there always has to be an even number. Okay? By trying to write down a few examples of that, representing the identity. For instance, I can represent the identity as the transposition 2,4 followed by the transposition 2,4. So I'm just repeating the same transposition. Transpositions, of course, are self-inverse. If you swap the positions of 2 elements to return everything to the beginning, you just swap them again. You see the identity is represented as a product of even number of transpositions. This theorem is proving that that is always the case. And it proves it in a very nice way, in a kind of an induction way. So he starts off with, so here's our identity represented as a product of R transpositions. So our goal here is to show that this value R must be an even number. What we just do is we look at the right-hand edge of this product. So on the right-hand edge, we see TR minus 1 composed with TR. TR minus 1 composed with TR, if you look at the final, if you look at TR, we'll suppose that TR is the transposition AB. Okay, so transposing objects A and B. TR minus 1, this is an exhaustive list of the possible forms of TR minus 1. Either TR minus 1 is the same as TR, or the first entry is the same as the second entry of TR, but the second entry is different, or both entries are different to the entries in TR, or the first entry of TR minus 1 is the same as the A, and then there's a different one in the second entry. Okay? So TR minus 1 must be one of these 4 forms shown in this product chart. And what these equations are showing that either, well, if they're both the same, those are inverse elements of each other, so they'll cancel to give you the identity. So that would reduce this product down to be a product of T to the R minus 2, sorry, a product of R minus 2 transpositions. Tau 1 composed with tau 2 all the way up as far as tau or minus 2. So we can cancel those last 2 if they're of this form. So that case will be covered by an induction, because that reduces it to a smaller number, a product of a smaller number of transpositions, which by induction we know will have to be an even number of transpositions. Where they don't cancel then, what it is possible to do, and here we're concentrating on this label A, it is possible to re-express the product of these 2 transpositions in such a way that the label A is moved to tau R minus 1, and it's removed from tau R. Okay? So you look at the final transposition, We pick out the first label in it, A. Either tau r cancels with the one that came before it to reduce it to a smaller size, which is covered by induction, or we can re-express it to move this label A out of the very last position. And that step we can keep repeating. Okay? We can now look at the pair tau r minus 2 composed with tau r minus 1. We see A as the first label in tau r minus 1. Again, we can either cancel tau r minus 1 with the one that came before it, tau r minus 2, or we can move the label A into tau r minus 2. So we have this procedure which is bit by bit taking the label A, which is mentioned here, and moving it into the previous one all the way. It may be that along the way we reach a cancelling pair, which reduces it down to r minus 2 transpositions, which is covered by the induction case. So r minus 2 must be even, therefore r must be even. If that doesn't happen, A will have moved all the way until it's sitting in the transposition tau 1. But that's a contradiction. How could we move the label A all the way until it's sitting in tau 1? And so A is mentioned in tau 1, but it's not mentioned in any of the other ones. But you see, this is supposed to be the identity transformation. So you can't have A not being mentioned by tau r up to tau 2. So the product of those transpositions would leave A fixed, because none of them mention A. And then the last transposition that's applied, tau 1, that moves A. Well, then, this cannot be the identity transformation. So that tells us that that can't happen. It can't be possible to move the label A all the way to the front without reaching a cancelling pair somewhere along. That's the way the proof works. So the identity can only be represented as a product of an even number of transpositions. And then there's a corollary to that, although it's the theorem, really, that capitalizes on that. Using that fact, we can prove that as when we represent it as a product of transpositions, any permutation, it must either be an odd number of transpositions or an even number. Okay? So you can read through the proof there. It takes the general case where you might have a permutation represented differently as a product of transpositions. The question is, what's the parity of M and N? We're trying to prove they have the same parity, they're both odd or they're both even. And the way the proof works is it reduces it to a representation of the identity. And once you have the representation of the identity has to be even, that tells you that M and N have to have the same parity as well. It's a really nice argument, taking this general result, proving it with a nice detailed argument for a special case, the special case of the identity, and then the actual proof of the theorem just illustrates how you can reduce the general case to an instance of the case for the identity, which we've already proved.